Hi, I'm Dave from TRC. Welcome to our Heat Pump Boss series, Level Up Your Heat Pump Installs. We've got the tools, tips, and how-tos that will make you an expert heat pump installer. Today, we're going to focus on how to do takeoffs, installation surfaces, above and below grade walls, ceilings, attics, and floors. Let's dive right in. To prepare an accurate manual J, we need a clear picture of the home's thermal boundaries, the insulated surfaces that separate conditioned space from outdoors and unconditioned parts of the house. In this video, we will go through how to assess walls, floors, ceilings, attics, and below-grade assemblies, and how these details factor into the load calculations. Most heat loss in a home is through the insulation, but it's a straightforward effort to get the home's insulation levels into the manual J calculation. The key is not to make assumptions based on building vintage or guesswork. Make sure that the R values we put into the load calculation match the house. Let's start with exterior walls. First, assess if there are different types of wall assemblies and prepare to capture each. Likely the bulk of the walls are all one type, but there are often a few sections of a home that have different construction. Either they were built at different times as an addition or renovation, or they're just a different part of the house, like an exposed walkout basement wall. For each type, document the wall type, either framed or masonry, along with visible or inferred insulation levels. Next, document how much wall area there is of each type. While avoiding guesswork should be a general rule of thumb, walls often require at least some educated guesses, because not all aspects of each wall type can be visually confirmed. Let's talk about framed walls. The first piece of evidence for a wall's insulation is its overall thickness. You can check this at a door or window jamb. Framed walls are typically built with a standardized frame depth. 2x4 or 2x6 are the most common. Be sure to add in the sheathing and drywall. And remember, a 2x4 framed wall is just about 5 inches thick, and a 2x6 is just about 7 inches thick. Next, see if you can confirm the R value of the cavity insulation. 2x4 walls are most commonly R13. Newer construction might have R15, and some very old walls might have R11. You may be able to confirm the R values by taking off a light socket plate and looking in, but sometimes you need to make an assumption by the home's vintage here, or by talking to the homeowner to see if they know. It's also worth looking for evidence of spray foam or dense pack insulation in the cavity, as those typically have higher R values. One critical wrinkle is newer construction methods commonly use exterior rigid insulation in addition to the cavity framing insulation. This is typically on the outside of the wall, 1 or 2 inches thick, though it could be done thicker. It makes a substantial difference to the overall wall assembly's insulation caliber. You can often tell if it's included by looking at the windows. If they're recessed back an inch or two, that's typically because they're resting on wood framing, and the external rigid insulation is coming out an extra inch or so. There may be other hints at transitions in the external sheathing or with external outlets. Details like framing width, 16-inch on center or 24-inch on center, have small impact on overall assembly U factors. If you see evidence of 24-inch framing from construction documents, thermal camera imaging, or from attic or basement where some wall elements are more exposed, document that for the manual J. If not, assuming 16-inch on center is just fine. Finally, there are some uncommon framed assembly types that can result in substantially better insulation. Double stud walls and staggered stud walls will have a continuous layer of insulation on the inside of the wall within the cavity. Structural insulated panels can also provide superior insulation levels for their thickness. These are very difficult to identify without the help of thermal camera or construction documents that tell you what's inside. But one giveaway for double or staggered stud walls, they're almost certainly thicker than the common 2x4 or 2x6 thickness. If you see walls that are more than 7 inches thick, put a little more time into trying to figure out what's between the sheathing and the drywall. Similar guidance applies to extremely old walls, with either lath and plaster interiors or brick facades. In each case, you need to work a little harder to confirm what's behind the scenes, using a thermal camera to see stud framing, or look from above in the attic or below at the band joist to give you a sense of what's inside the wall. For masonry walls, we're going to look for insulation on the outside and the inside of the masonry. For above grade masonry walls, they're almost always going to be insulated somewhere. Never assume zero insulation. You'd be able to feel the cold through such a wall easily. Exterior insulation is often hidden under the siding. Similar to external insulation for framed walls, look at the windows. If they're recessed, that's a common indication of external insulation. You can also look at transitions in the sheathing or at the outdoor outlets. Or you may need to ask the homeowner if they had it installed or have any construction documents to help. For internal insulation on masonry walls, it's often framed wood on the inside of the wall, covered with drywall. Other times it could be spray foam layer with furring strips to hold the drywall. Looking at overall wall thickness behind socket plates and around wall transitions can give you hints of what insulation levels are present. Next, let's look at ceilings and attics. Just like with walls, first confirm if there is more than one ceiling type to be modeled, and capture the surface areas and insulation characteristics of each. Most homes are insulated at the ceiling, with a vented attic above, and those are the easiest to get information about, so let's start there. Carefully find your way to the attic. For rolled batt insulation, the R value may be printed on the paper backing, or you can roll some back and capture its thickness. For blown-in insulation, see if the installers left insulation depth markers, those little rulers along framing elements. If not, you can use a depth gauge to prod through the insulation and take a measurement. Avoid actively disturbing the insulation as much as possible. Then, the insulation's R value will depend on the type of insulation. You can look this up by insulation type or by a number of reputable online tables. But for the most common types, fiberglass or rock wall batts will be about R 3.2 per inch. Blown-in fiberglass is R 2.2 per inch. Blown-in cellulose is R 3.4 per inch. If you have other insulation types, such as spray foam or dense pack cellulose, try to determine its type, thickness, and R value per inch from suppliers, construction documents, or trusted online resources. Next, some attics are invented and insulated below the roof deck. For these, the insulation is commonly either a dense pack behind some form of netting or with spray foam. You should be able to tell the thickness of either type by looking at places of transition or around exposed framing elements. Then there are cathedral or vaulted ceilings. Like walls, the insulation is fully contained between the roofing material and some form of internal drywall or sheathing. These are the hardest to determine. See if you can make out the total roof thickness as a general guide, perhaps at a skylight, or some transition point in the roof line, or at the gable end. See if the homeowner knows, or if there are construction documents you can refer to. A thermal camera again might give you some information. It may be SIP, or a framed roof with cavity fill. There may be a continuous insulation layer, or there may be an air gap for venting. Overall, with ceiling and roof type, you will often need to make an educated guess. Below-grade assemblies, things like basement walls, slab-on-grade floors, and foundation systems behave differently than above-grade surfaces. While it's true the surrounding soil moderates temperature, insulation levels still matter below grade. It's important to document whether the basement walls are insulated, where the insulation is located, and how continuous it is. For basements and crawl spaces, the first step is to classify the space and how you plan to model it. You can either model the below-grade space as within the conditioned envelope and model the heat transfer across the below-grade floors and walls, as well as any above-grade components for walkouts or having the top of the wall exposed. In this instance, you don't model the heat transfer across the basement ceiling or the first floor, and you include the area as part of the conditioned floor area. Alternatively, you can just model the floor above the unconditioned basement or crawl space. If doing so, you can entirely skip the below-grade surfaces and just model the basement ceiling, or first floor, that separates them. Obviously, if the basement is actively conditioned, you need to use the first approach, but if not, you can make the choice. The math will typically end up with similar results to each other. But typically, it is more accurate to actively model the basement's volume and perimeter surfaces. The only time we're modeling the floor above unconditioned basement or crawl space is the better choice is when the layer between it and the living space is well insulated and air sealed, thus truly unconditioned. For below-grade walls, follow the same principles described with above-grade masonry walls. The one key difference will be spotting external insulation. It may poke up above grade, outside of the building, but it also might not extend full depth of below-grade walls. Sometimes it only goes 2 to 4 feet down. Then there's also the potential for insulation below the basement floor. For both, the only way to fully know is to consult construction documents, if they're available, or make assumptions based on building vintage and what the norms and code requirements were at the time. More recently built homes are much more likely to have insulation below grade. Now, let's move on to floors. Just like walls and ceilings, first determine if there are more than one type of floor in the home, and capture the surface area and insulation caliber of each. For floors over unconditioned space, such as the floor above a garage, cantilever overhangs, or parts of the conditioned area built on stilts, the insulation is going to most commonly be cavity fill between framing. It likely won't be exposed for visual inspection. R19 cavity fill is quite common for New York for these surfaces, but again, look for construction documents. Overall assembly thickness, thermal imagery, access points with recessed lighting, or clues to guide you to what's really in the assembly. If you're modeling a floor over an unconditioned crawlspace or basement, you can typically visually inspect the insulation and determine its total R value. For slab floors, or below-grade floors, you typically can't see if there's insulation below the slab. Again, consult construction documents if available, talk to the homeowner, and consider when the home was built to help guide you. For each of these, you're also documenting the surface areas of each assembly type. A tape measure or laser measure is invaluable for getting these dimensions right. One little confirmation trick: make sure the total ceiling area and the total floor area are the same, or nearly so. Each part of the house that has a floor has a ceiling somewhere above it. Similarly, calculate a wall-to-floor area ratio. It should be between 0.4 and 0.55 in most cases. It will be a lower number for less complicated geometries like simple colonials, and more for homes with L shapes or lots of dormers or other features. And one other thing about surface areas for walls and ceilings: you typically will model the gross area, then assign a window, door, skylight to that, and the software does the math for you. So for example, if you have a 20-foot long, 10-foot high wall with a 36 square foot sliding glass door in it, model 200 square feet of wall, then assign the sliding door to it. The Manual J program will model heat loss across 164 square feet of wall and 36 square feet of window for that full section. Once all the surfaces are documented, confirm that the thermal boundary is continuous and logically defined. Every part of the home must be either inside the thermal envelope or outside of it. Be careful not to model heat transfer through surfaces that are entirely within the thermal envelope, such as interior walls and floors. Make sure you've accounted for odd areas, like dormer sheds, the garage to home surfaces, and around uninsulated porches or decks, to name a few. Get all the assembly types, insulation, R values, and surface areas written down. Clear documentation prevents modeling errors and helps produce accurate load calculations and enables correct equipment sizing. Thanks for diving in with us on how to do takeoffs, insulation surfaces, above and below grade walls, ceilings, attics, and floors. Remember, we're here for you at cleanheatconnect.ny.gov with more videos, resources, guides, and best practices. Hope to see you in our other sessions as we complete better installations together, one project at a time.